Imagine, right, you're in a self-driving car. It's doing, say, 70 miles an hour down a multi-lane highway.
Okay, setting the scene. I like it.
Yeah, and a plastic grocery bag just blows across the asphalt. Now, a human driver, we barely blink at that. Maybe we just ease off the accelerator a tiny bit.
Right, it's not a threat.
Exactly. But if the car's onboard vision system, like if it misclassifies that swirling plastic bag as a darting pedestrian, it slams on the anti-lock brakes.
Which could cause a massive 10-car pileup.
Yeah, and that terrifying, razor-thin margin for error, that is the difference between theoretical math and applied AI.
Which is actually the perfect scenario to frame where we are today. Because for those of you listening, you can basically consider this the grand finale. This is the final lesson of your graduate deep learning journey.
We made it. It's been a long road for everyone tuning in.
It really has, because up until now, we've been operating in a controlled laboratory. We started with the really broad strokes of artificial intelligence and machine learning.
Oh man, all the way back to diving into the raw math of single perceptrons.
Yeah, exactly. The shallow and deep neural networks.
And we agonized over the calculus of optimization, right? Like gradient descent.
Oh, yeah, everyone's favorite. But then, we gave these networks architecture. We explored how convolutional neural networks, or CNNs, how they give models spatial awareness.
Right, the spatial stuff. And then how recurrent neural networks, the RNNs, give them sequential memory.
Exactly. But those were, well, they were isolated tools, just building blocks. So
Yep.
today's mission, our focus for this deep dive, is to pull all of those modules together.
We're finally moving out of the lab.
Exactly. We're moving into applied end-to-end systems that actually have to navigate the chaos of the modern world. We are going to synthesize computer vision, generative adversarial networks, and recommendation systems.
Both the statistical ones and the deep learning ones.
Yeah, the whole spectrum.
Okay, let's unpack this. I want to start with giving machines the ability to see. Computer vision.
A huge topic.
It is, yeah. And we already know from our earlier deep dives that CNNs, they learn these hierarchical visual features. Like they look at raw pixels, find a vertical edge, combine those edges into a texture.
Right, and then combine the textures into, say, a wheel or a bumper.
Yeah, until eventually it recognizes a whole car.
Well, in theory, yes. But deploying that in the real world, outside the lab, it exposes a massive vulnerability.
Because the real world is messy.
Extremely messy. Deep networks, they require gargantuan amounts of perfectly labeled data to learn those hierarchies robustly. So if you train a CNN on a small, perfectly clean data set of cars, it will just take the path of least resistance.
It gets lazy.
Basically, yeah, it memorizes irrelevant artifacts. So it might learn that the label car means an object perfectly centered in the frame on a sunny day, rather than, actually learning the physical shape of a chassis.
Yeah. Oh, I see. It's almost like a student studying for an exam. Like if you only ever review your flashcards sitting in total silence at your own desk in your bedroom, you might completely panic and fail if you have to take the actual test in a loud, freezing exam hall.
That is a great analogy.
Because you inadvertently memorize the environmental context,
Right. Yeah,
not just the material.
precisely. And to stop a neural network from doing that, we use something called image augmentation. We deliberately inject chaos into the training data.
What does that look like in practice?
Well, we take an original image of a car and we apply label-preserving transformations, meaning we change the image without changing what it is.
Like flipping it.
Yeah, we flip it horizontally, we randomly crop it, maybe scale the width and height down to, say, 200 pixels. We might rotate it, or even warp the brightness and hue.
So even if the picture is suddenly upside down, slightly blurry, and, I don't know, tinted purple, we are forcing the network to understand that the label is still car.
Exactly. It has to look for the invariant features, like the geometric relationship between the wheels and the roof. It can't just rely on perfect lighting anymore.
That makes a lot of sense. You're forcing it to actually understand the object.
Right. And this creates a much more robust model. But here is the catch. Even with infinite augmented data, training a massive deep architecture like ResNet from scratch takes a colossal amount of computing power.
Which is a problem because most developers don't have like a Google-level server farm in their basement.
No, they definitely don't. And this brings us to transfer learning, which honestly is arguably the mechanism that truly democratized AI.
Okay, so how does transfer learning actually get around the server farm problem?
Well, instead of initializing a network with completely random weights and teaching it to see from absolute scratch, you take a source model.
So a model that's already trained.
Yeah, let's say ResNet 18 or ResNet 50. Those have already been pre-trained on ImageNet, which is this massive data set of millions of images.
Got it. So it already fundamentally understands edges, textures, and geometry.
Exactly. And then you adapt this into your target model.
I want to break down the actual mechanics of that. Because if I'm building a specialized application, say a system that scans a conveyor belt and categorizes items as either hot dog or not hot dog,
The classic example.
right? How do I bend this massive, generally pre-trained network to my tiny, highly specific problem?
So you literally copy the pre-trained parameters over. But, and this is key, you freeze the earlier layers of the network.
Freeze them, as in they don't update during training.
Exactly. Those are the layers acting as your general feature extractors. They find the curves and edges. You don't want to mess up their math.
Makes sense.
Then you essentially amputate the final output layer, the part that originally categorized 1,000 different ImageNet classes. You toss it out.
Okay, and replace it.
Yes. You graft on a brand new output layer designed just for your specific categories, in your case, hot dog and not hot dog.
Oh, wow. And then I just run gradient descent on that single final layer.
Yep. Using a very small learning rate on your specific data set, you are essentially teaching a brilliant, generally educated brain how to perform one highly specific new task.
That is so cool. It totally solves the classification problem. But wait, knowing if a hot dog or a pedestrian is in a picture is only half the battle, right? Like going back to our self-driving car. A binary yes or no, there is a pedestrian somewhere in this frame is completely useless to the car.
It needs coordinates.
Yeah, it needs to know exactly where the pedestrian is so it doesn't hit them. So we have to move from just image classification to object detection.
We're shifting from knowing what is there to knowing what and where. And to do this, we use bounding boxes.
Those little rectangular borders drawn around objects in AI videos, right?
Exactly. Usually defined by their center point coordinates plus their width and height, or sometimes the corner coordinates. And to actually find these objects, modern systems generate thousands of candidate boxes called anchor boxes.
Thousands of them.
Yeah, across the whole image, at all different scales and aspect ratios.
Wait, hold on. If the system is projecting thousands of overlapping anchor boxes across every single pixel, doesn't it just drown in a sea of overlapping noise?
It's a massive amount of data, yes.
Because if there's just one traffic light, the network might generate 20 boxes that all slightly overlap that same light. How does it mathematically filter that mess down to one clean detection?
That overlap problem, that is the core challenge of object detection. And we solve it in two steps. First, during training, we evaluate every single anchor box using a metric called intersection over union, or IOU.
Let me guess. We measure the area where the predicted box intersects with the true ground truth box, and then we divide it by the total union area of both boxes combined.
You nailed it. You divide the overlap by the total footprint. If that IOU ratio is high, the anchor box is considered a positive match.
It actually caught the object.
Right. But if it's low, it's a negative anchor. We just treat it as background.
But wait, even after you filter out the background, you still have multiple positive boxes swarming that same traffic light.
And that is where the cleanup algorithm comes in. It's called non-maximum suppression, or NMS.
On maximum suppression, okay.
It is this really elegant, greedy sorting mechanism. First, the network assigns a confidence score to every surviving bounding box. We take all those boxes and rank them from highest confidence all the way to lowest.
Okay, so I grab the box with, say, a 99% confidence score, I lock it in, and then I look at the rest of the list.
Exactly. You look at any other box that overlaps with your 99% box. If the overlap exceeds a certain threshold, let's call it epsilon, you just throw the lower scoring box away.
You suppress it.
You suppress it because
Okay.
you assume it's just a duplicate detection of that exact same object. Then you move to the next highest scoring box that survived, lock that one in, and repeat the sweep.
Until only the distinct ones are left. It's ruthless but effective.
Very.
And, understanding how these detection architectures evolved really exposes that brutal trade-off between accuracy and compute cost. Like the whole history of the RCNN family is basically a war on bottlenecks.
It really is. I mean, it started with vanilla RCNN. The bottleneck there was that it used an external non-neural algorithm called selective search.
Which did what exactly?
It just guessed about 2,000 potential regions of interest in an image, and then it physically cropped those 2,000 regions out, ran every single one through a standard CNN independently, and then used a support vector machine to classify them.
2,000 separate times.
Yeah.
For a single frame of video. That is computationally absurd. You'd be processing, what, 1 frame a minute?
It was incredibly slow, too slow for any real-world application, which led to fast RCNN.
Okay, so how did they speed it up?
The breakthrough was reversing the order of operations. Instead of cropping the raw image first, fast RCNN runs the CNN over the entire full image just once.
Oh, so you get one massive feature map of the whole scene.
Yes, a very rich feature map. And then you apply your region proposals directly onto that feature map.
How does it read them if they're all different sizes, though?
Through a mechanism called row-I pooling, region of interest pooling. It takes those arbitrary-sized proposed regions on the feature map and mathematically squashes them down into fixed-size inputs. That way, the final layer can actually read them.
That's smart.
It allowed them to use a multitask loss function. So they were updating the network for both classification and bounding box coordinates simultaneously.
But wait, fast RCNN still relied on that clunky external selective search algorithm to guess where the objects were in the first place.
Exactly. That was still a huge bottleneck. To make it truly efficient, they had to bring the proposal process inside the neural network itself.
Which birthed faster RCNN.
Yes. They completely replaced the external algorithm with a region proposal network, an RPN. So the network actually learns to look at its own feature maps and predict where objects are likely to be. It became a fully end-to-end system.
And yet, for a car going 70 miles an hour, even faster RCNN isn't quite fast enough. You need real-time, high frame rate processing, which is why the field pushed toward SSD, right? Single-shot detectors.
Right. Single-shot detectors toss that whole region proposal step out the window entirely. They don't look for regions and then classify them sequentially.
So what do?
They predict the object classes and the bounding box offsets directly from the feature maps in one single pass. And crucially, they make these predictions from multiple feature maps at different resolutions at the same time.
Oh, I see. Meaning a high-resolution map catches a tiny pedestrian way down the road, while a low-resolution map catches the massive truck right in front of the bumper, all calculated in a fraction of a second.
Exactly. It's incredibly fast.
Yeah.
But, and this is a big but, this entire pipeline, the classification, the localization, the bounding boxes, it all relies on a huge assumption.
What's that?
That you have massive data sets of perfectly labeled human annotated ground truth to train on.
Which is incredibly expensive and slow to generate.
Right. So what happens when we reach the limit of human annotated data? If these deep learning models are data-hungry engines and we simply run out of fuel, the only solution is to teach the machine to manufacture its own fuel.
Oh, wow. Okay, here's where it gets really interesting. We have to teach them to synthesize reality.
Generative adversarial networks, GANs. We move from a network that just analyzes the world to a network that can literally hallucinate it.
I love this topic. I always hear the analogy of an art forger and a police detective for GANs. But given how complex these networks are, maybe let's look at it more like a high-tech counterfeiter trying to beat a casino's automated currency scanner.
I actually think that fits the mechanics much better. So the generator in our GAN is the counterfeiter. But it doesn't start with paper and ink. It starts with a latent vector, which is literally just a string of random numerical noise.
Just noise.
Pure noise. Its job is to mathematically map that random noise into a synthetic piece of data, say an image of a $100 bill.
And the discriminator is the casino scanner.
Exactly. It acts as a binary classifier. We feed it real $100 bills from our training data, and we also feed it the fake bills produced by the generator.
And it uses binary cross-entropy loss to try and output a 1 for the real bills and a 0 for the fakes.
Right. And here is the key mechanism of how they learn. Alternating updates. It's a minimax game. First, you freeze the generator. You train the discriminator to get really good at spotting the current batch of fakes. It learns that, oh, the fakes have slightly blurry watermarks.
Okay, then what?
Then you freeze the discriminator. You feed the generator's fakes into the scanner, but you calculate the loss based on how badly the generator failed to fool the machine.
Oh, so the generator takes that error gradient and updates its own weights, learning to make the watermark sharper next time.
Exactly. They're locked in this evolutionary arms race. But what's fascinating here is that this introduces a massive mathematical headache. Because throughout your whole deep learning course, we've basically treated loss like gravity.
Right. Minimizing loss was just like rolling a ball down a static hill until it rested at the bottom.
But in a GAN, the hill's moving.
The landscape itself is shifting.
Continuously. When the generator improves, the discriminator's error instantly spikes. even if the discriminator hasn't changed its weights at all. You aren't minimizing a static error. You are trying to find a balance, a Nash equilibrium in a dynamic game.
Which sounds incredibly unstable.
It is. If the casino scanner gets too good, too fast, the counterfeiter's loss gradient just flatlines, it learns nothing and basically gives up. And if the counterfeiter gets too good too quickly, the scanner just starts outputting random guesses.
So how do you stabilize that?
Researchers developed architectures like DC GANs, deep convolutional GANs. And this is where the math we learned earlier gets turned completely inside out.
Wait, how so?
Well, in a normal CNN, convolutions compress a large image down into a small, dense feature vector, right?
Yeah.
But the generator in a DCGN has to do the exact opposite. It starts with a small, latent vector of random noise and has to expand it into a high-resolution image.
Oh, right. So how does it upscale?
It uses transposed convolutions. Instead of a kernel sliding over pixels to extract a single feature, a transposed convolution takes a single feature and broadcasts it outward, painting it across multiple pixels.
That's wild.
And when you combine that with techniques like batch normalization to keep the signals from exploding and leaky ReLU activations to ensure gradients keep flowing even when the network is unsure, DC GANs allowed us to actually synthesize photorealistic images.
And the applications we see now from this are staggering. I mean, generating synthetic faces that don't exist, super resolution, where the John hallucinates the missing pixels in a blurry image to make it crystal clear.
Photo inpainting, where it seamlessly repairs corrupted data, even generating full 3D objects.
It totally solves the data bottleneck we talked about.
Mm-hmm.
But, it creates a new, arguably more dangerous problem.
Information overload.
Exactly. When AI can generate infinite synthetic content, images, text, videos, the human user is suddenly drowning. A platform with 10 million synthetic videos is useless if you can't find the one video you actually want to watch.
Which perfectly forces us into the final module of the applied AI ecosystem, recommendation systems. We have to curate the chaos.
So how do we curate it?
First, we must distinguish between search and recommendation. Search is a query-driven retrieval system. You explicitly type how to fix a leaky faucet, and the algorithm matches keywords.
Right, but recommendation is personalized, it's proactive.
Exactly. The system predicts what you want before you even ask for it. And it does this by mining the user item interaction record. It builds a profile based on two types of feedback.
Explicit feedback and implicit feedback, right?
Yes. Explicit feedback is obvious. You give a movie 5 stars or you hit the thumbs down button.
But explicit feedback is rare, isn't it? Users are lazy. I rarely rate things.
Most people don't. That's why the real goldmine is implicit feedback. The system just watches your behavior. Did you click the thumbnail? Did you watch for 10 seconds and abandon it? Or did you binge watch 4 hours straight?
Did you scroll past it slowly?
Exactly. All of those microinteractions get dumped into a massive user item matrix. Imagine a giant spreadsheet where every row is a user and every column is a piece of content. The cell where they intersect hold your engagement score.
But wait, there's a glaring mathematical flaw there. Scarcity.
Yes. The matrix is almost entirely empty. A platform might have 100 million videos, and you have watched maybe, 500 of them?
So 99.9% of my row is just missing values.
Right. The system has to figure out how to accurately fill in those blank spaces to predict what you'll like.
How do statistical approaches actually do that? Because finding a user similar to me seems straightforward, but how does the math handle millions of empty cells?
The most powerful classical approach is collaborative filtering, specifically matrix factorization. Instead of trying to process the giant, mostly empty matrix, the algorithm mathematically decomposes it into two much smaller, dense matrices, one representing the users and one representing the items.
So by compressing the matrix, you force the algorithm to discover latent features.
Precisely. The algorithm might discover a hidden mathematical dimension that strongly links you to a specific cluster of movies. It doesn't know that the dimension is called, say, sci-fi action with strong female leads.
It just knows the numbers line up.
Right. It just knows that mathematically your vector aligns perfectly with the item vector for that genre. It multiplies those latent vectors together to predict your missing rating.
But let me push back on that for a second. Is predicting a rating actually the goal? Let's say matrix factorization perfectly predicts that I will give a deeply depressing documentary 4.9 stars.
Okay.
I might objectively recognize it's a great film, but on a Friday night after a long week, I don't want to watch it. I won't click it.
This is a crucial distinction in applied recommendation systems. Predicting a rating, which we evaluate using metrics like root mean square error or RMSE, is a prediction task. But real-world recommendation is a ranking task.
Because the user only ever sees the top 5 items on their screen.
Yes. The system doesn't just need to find good items. It must rank them so the most engaging ones are at the absolute top of your feed. That's why we evaluate these systems using ranking metrics like precision at K, which measures how many of the top K recommendations were actually relevant.
Or NDCG at K, right?
Yeah.
Which goes a step further and heavily penalizes the system if the best item is placed at position 5 instead of position 1. Order matters.
Exactly. Order is everything. So we have these classical statistical approaches. But to truly synthesize this course, to bring this entire graduate deep dive full circle, we have to look at deep learning collaborative recommendation systems.
Oh, this is where everything we've learned merges.
It is. We take the deep neural architectures originally designed for other domains, like vision, and we aim them directly at human behavior.
The Kaser model is the perfect example of this, isn't it? It uses vertical convolutional networks to analyze a user's history.
It does.
But wait, we just spent the first half of this deep dive establishing that convolutions slide across pixels in an image to find visual edges. How do you apply an image processing kernel to a list of movies someone watched?
You have to rethink what a convolution actually is. A convolution is really just a mathematical operator that looks for local sequential patterns. In an image, the sequence is spatial pixels.
Right.
But in the Kaser model, the sequence is time.
A behavioral timeline.
Yes, we represent your recent history as a two-dimensional matrix. The horizontal axis is time, so maybe your last 10 interactions. The vertical axis represents the latent embedding dimensions of those items.
Okay, I'm with you.
So a vertical convolutional filter slides across this timeline, but it only looks at one specific embedding dimension at a time.
Oh, that is brilliant. Instead of scanning an image for a visual edge, the CNN is scanning my behavioral timeline for a psychological shift. It's watching a specific latent dimension, say, my preference for dense theoretical documentaries, and it's calculating if that preference is trending up or down over the last 48 hours.
It captures point-level sequential patterns in human behavior. The exact same calculus that finds the geometric edge of a pedestrian's silhouette in a self-driving car's camera feed is being used to track the real-time evolution of your subconscious preferences.
The math is universal.
It is, and that universality is really what brings us to the end of this journey. For you listening, just think about the magnitude of what we've covered. We started weeks ago with the sterile math of a single perceptron.
And today, we've looked at the end-to-end architectures that parse our visual reality, that hallucinate synthetic worlds, and that curate the personalized digital ecosystems we inhabit every day.
It is an incredible technological leap. But as we close out the course, I do want to leave you with one final structural implication to mull over.
Oh, a provocative thought. Let's hear it.
We have built these applied systems. Transfer learning allows models to share general knowledge. GANs allow models to generate infinite synthetic data to overcome human bottlenecks. Deep recommendation systems perfectly curate and distribute that data based on our behavioral timelines.
So all the pieces are on the board, and they are starting to connect.
Right. So consider what happens when they fully integrate. An AI generates hyper-personalized synthetic content. A neural recommendation system feeds that synthetic content to a human. The human reacts, generating new behavioral data.
And then that data is fed back into the system to train the next generation of models. We are rapidly building a closed loop.
We are, and it begs the question, what happens to the original human ground truth? When the data feeding the models is heavily influenced by the models themselves, does human behavior simply begin to mimic the AI's recommendations? Or is the AI just perfectly mirroring us?
Wow. Where does the machine end and the human begin?
Exactly. It's no longer just a question of optimization or loss landscapes. It's a question of architecture, and, well, you now have the tools to understand it.
Now that is a thought to keep you up at night. Keep questioning the architectures you build, keep exploring the math, and congratulations again on finishing the deep dive. We'll see you next time.